So we have some wonderful speakers here from UCD, the University College Dublin, to talk to you all about black holes and gravitational waves and other cool space stuff. And then we will have a quiz all about science, so pay attention. It's not like school, I swear. We have prizes that are slightly better than a CAO form. So first of all, I just have to thank our sponsors, which, well, obviously ILOFAR is hosting this event, which is the radio telescope right across the road. If you haven't heard of it, come have a look. And Trinity College Dublin, Science Foundation Ireland, and this is part of a Science Week event, and also ESA, which is the European Space Education Resource Office, which I don't expect anyone to have ever heard of, but it's sort of part of ESA, the European Space Agency. Which also brings me on to, we've got some really cool quiz prizes from ESA and ESO and lots of other acronyms. So yeah, pay attention. But first of all, I would like to introduce our first speaker, who is, I'm definitely going to get your name pronunciation perfectly, Dr. Niels Warburton. Niels Warburton, sorry, from UCD. He works in the UCD Relativity Research Group. He studied in Leeds, Southampton, MIT, and UCD. And yeah, I guess I'll just hand it over to Niels. So we'll just do a little bit of technical, amuse yourselves. Yeah, it's pretty short cable. You guys aren't very amusing. We are experiencing technical difficulties. Yeah.
Alright, thank you very much for bearing with us there. Thanks for coming out on this snowy day. Today, I'm going to talk to you a little bit about stuff that touched on the research that we do in my group. So here with myself, we have some of the PhD students in the group, with Ben, Leanne, Phil, Kevin and Josh. And upstairs, if you haven't already checked it out, we have some virtual reality kind of headsets you can put on and check out some of the features, and you can actually see some black holes and walk around them in the virtual world. Today though, my talk is going to be about black hole astronomy, which is how do we study and find these objects which are very elusive and basically completely invisible in the universe. How do we know they even exist, for instance? So I wanted to start with this picture, which is a multi-spectrum image that's taken with different telescopes, and the colour has been altered so we can see it. It's an image of the very centre of our Milky Way galaxy. So the reds are the kind of infrared light, and these come basically heat that's coming off in the centre of the galaxy. The yellow is the visible light that we would see, and the white is kind of the X-ray. And you can see that here there's this very bright region, and this is what we think of the heart of the centre of the galaxy. And here there's a massive black hole that lives right in the middle of it. But the question is, how do I know that? How am I confident there is really a black hole in the centre of our galaxy when, of this beautiful image, the black hole is precisely the piece of this image that looks like this? That is, it is completely black, as its name suggests. Of course, then the problem is the other thing that is out there in the universe that is completely black is just empty space, nothingness. So how can I tell nothing, which is not very interesting, apart from a black hole, which is an extremely interesting, most extremely interesting objects that we have in the universe. So my talk will be broken into three pieces, and then Ben will talk about the final section, which is about the research we do. The first one I should tell you a little about what actually is a black hole, all of its basic properties. And then the way we know black holes exist, because we can't see them directly, is how they influence things around them. And that can be how it influences light that passes nearby, how it can influence matter that's falling in or orbiting around the black hole, or in fact how black holes or particular pairs of black holes orbiting each other can disrupt and change the very fabric of space and time. And as I said, I will talk about these first three, we'll take a short break, and then Ben will talk about the space and time and gravitational waves we study in UCD. Okay, so what is a black hole? Well, a black hole is just an object that has become so massive that light cannot escape. So we know well on the Earth that although it's hard to get off, we can do it. It takes huge technological achievements, but if you build a big enough rocket, you can get off the Earth and escape from this gravitational field. If you then pile more mass on and consider something like Saturn, a much larger celestial body, well, you can still escape from the gravity of Saturn, you just need a bigger rocket. This eventually, though, breaks down. If you keep adding more and more mass, it doesn't matter how much, eventually there comes a point where once you build a rocket big enough, there is no rocket big enough you can build to actually escape through the gravitational field. And so a black hole is a region of space. It's a, if you want, the region is a sphere out there in space. Where gravity is so strong that not even the very fastest thing in the universe, which is light, can escape from it. And it's defined by this thing called the event horizon, which is the spherical region which you can go into, but you can never come back out from. And so that broadly then is what a black hole is. The next question is, how do you make a black hole? How do you get on the universe? It's really about density. And the requirement is to squeeze a lot of mass into a very small space. So as an example, if you were to take the Earth and find some way to squeeze it to the size of a 1-cent coin, it would become a black hole. So it's not necessarily need lots of mass, you just need a lot of it, or any amount of mass, but in a very, very tiny, confined space. Obviously, this is not a practical example, it's obviously very difficult. I don't know any way you could squeeze the Earth like that. And so in practice, the only way you can take an object and squeeze it into a very small volume is to add more mass, increases gravity, which increases the squeeze, and eventually you'll get enough matter in a region to form a black hole. And interestingly, just as a side note, what would happen to the solar system if you were to take the Earth and squeeze it down to the size of a coin and it collapses to become a black hole? We have this idea that black holes would just suck in everything around them. But this isn't the case. If you took the Earth and squeezed it down to the size of a little 1-cent coin, then the Moon would just continue to orbit that 1-cent coin. Nothing would particularly change about it. The Moon is sufficiently far from that as far as it's concerned, nothing has changed at all. These minor changes. Even more, the little black hole Earth and the Moon would continue to orbit the Sun. Again, nothing would really change. For us, we've lost our home, but the solar system remained unchanged. And so the key thing here is we have this idea that black holes can suck in everything. It's not really true, and it's only really true when you get very close, when the gravity gets modified. And this is a good thing, because as I mentioned, we have one black hole in a similar galaxy, a massive black hole. But in fact, our galaxy has millions of black holes in it. But that shouldn't concern us, because they're all very far away. And so their influence is no different from, we shouldn't be worried about stars in our galaxy, we're not worried about black holes for that same reason. And so black holes, in general, don't really suck on things unless you have to be very close when the gravity is modified. And by really close, I do mean close. So if the Earth was the size of a coin, you could be out, this distance from that coin, and you'd be fine, in principle. As I said then, the only way really to make a black hole is to get enough squeezing force, in this case gravity, which is the force that always attracts to more matter. And to do this, you need to add more and more mass until you have enough force to crush it down into a small region. How much? Typically about 2 solar masses. So if you take 2 suns, and you could ignore the fact that they are currently fusing and there's radiation pressure, these would then collapse into a black hole, which I've pictured here. Now, as I said, if you just took 2 suns and smashed them together, you wouldn't get a black hole immediately. The sun is going through nuclear fusion and is radiating, and that supports the pressure, fights against the gravitational pressure. But if you let those cool down, then that's the amount of matter you would need. Typically, though, to actually do this, you need something like a 10, 15 solar mass black hole, which will go through a violent explosion, and what's left will collapse into a black hole. Okay, so how do we know black holes exist? Well, one of the features that Einstein's theory of gravity taught us, his theory of general relativity, is that matter bends the space and the time around it. And one of the effects that he predicted, that was then measured, is that the passage of light from a star, so here we have some star, it releases some light, it travels along a path. As it gets near the sun, that path is bent by the curvature of the space and the time. And so you can see this light is just following, if you imagine this as a curved surface, it's just following the kind of straightish line it can in this curved surface. From our perspective on Earth, though, that star will, if you're looking back along that light ray, will appear to be over here. And so if you're looking at a star which is very close to the sun, its position will appear to have moved in the sky. Now, of course, this is a tricky experiment to do, because in order to do it, you have to look at stars which are very near the sun. And the sun is a star; it's much closer, much brighter. You can never do this. The only time you can get away with doing this experiment is this wonderful cosmic coincidence where the moon is just the right size and just the right distance that once in a while it will block out the sun. And then when that happens, when you're lucky enough to see it, you can see the atmosphere of the sun, but you can also see the stars that appear around it. And so, as I said, this is one of the predictions of Einstein's theory, and this was then measured famously back in 1919 by this guy Arthur Eddington, an expedition to the southern hemisphere. This is one of the slides. There's some stars in here, and what happens, you can see that the moon has blocked out the disk of the sun. You can actually see a solar eruption on the surface, but these stars, when carefully measured, were slightly moved from their position that you would expect them to be in when the sun wasn't there, basically. It's interesting to note that this is what made Einstein famous. We have this image of Einstein as this great genius, of this kind of archetypal genius. It was this that really shot into fame in the kind of public eye, and there's this very famous newspaper clipping from the New York Times that says that the lights are askew in the heavens, and the men of science are more or less agog over the results of the Crick's observation, and Einstein's theory triumphed. If anyone's curious, because I didn't know, agog means very eager and curious to hear or see something. And so this really kind of set him off on this life of fame. Okay, so that's the influence of light. And as I said, if you look at this image, the actual change in here is absolutely tiny. You cannot see it with the eye, it's very carefully measured. For a black hole, though, as always with black holes, that can be taken to the extreme. And so now we can see an experiment where somewhere in here we believe maybe there's a black hole. Here we have the Earth, where we're going to take our measurements, and here we just have the night sky. Black holes can bend light substantially. So in that previous image I showed you before, there was a big angle, but that was really just exaggerated for making the picture. This is the correct kind of amount of bending you can get from a black hole. So if you're looking across here from the Earth, you will actually, instead of seeing this star over here, you'll see this little galaxy down here. But it gets even more extreme. Light can leave from here, travel along this path, but it can also leave from here, do a complete orbit around the black hole, and come back to you, which is something that just completely doesn't happen in our solar system. You need this extreme, strong gravity. And indeed, if you were just outside the event horizon and you lit off a torch, even though you're at the back of the black hole, which is this little region here, let's say, the light could actually go all the way around and come to the Earth. That is to say, when you're looking at a black hole, you'll see this black disk, but some of that disk is the back of the black hole. So you can see the behind of it because of the motion of gravity, the bending of the light by the gravity. And so here, I've just drawn, this is where the event horizon would be. So these are all, I did these calculations quickly. Those are the correct paths of the light around the black hole. So that's just a kind of sliced through an image. What would that actually look like in practice? Something like this. So this is a computer simulation. We have a starry background with the night sky. Obviously, this object in the middle is the black hole shadow we normally refer to it. It's weird to talk about seeing a black hole, you really see it. As I said though, points on the back, points here, are really looking at the back of the object. What's interesting as well is you get multiple repeated image inside here. So for example, this star and this star are in fact the same star in this image. There's an infinite number of these as you go around. And in general, you'll find there are stars on the outside which are matched by a star on the inside of this ring, which is known as an ensemble. So this is one of the ways that it's kind of clear that a black hole exists. And perhaps this isn't one of the more obvious ways. There's something black and dark in the middle. You get these kind of violent distortions of the light around. So some of you might have seen recently, there was this big announcement by the Event Horizon Telescope of the first direct image of a black hole. And that's this beautiful image taken here. You can see it bears some resemblance to this. Remember, this is a computer simulation. The reason it's not as good as this is just this is the first ever image we've taken. It's the first time we've ever tried to do this. It took a global combined effort of scientists all over the world, telescopes based all over the planet, to build a telescope that was effectively the size of the planet to observe this object, which is in not our own galaxy, but another one nearby, another massive black hole. over time, we will improve our techniques, and the image will sharpen, and you'll get an image never quite as good as this, but something more approachable. The other difference here is that this image, these dots of light, are stars in the background. The light here is coming from accreting matter, so there's matter which is falling onto the black hole, getting very hot, and the light is coming off of it. Some of that light will come directly to your eye, but some of it will be bent around by the black hole in a similar fashion to here. But it certainly has the key feature of black hole, as this black region in the center. Okay, so that's influence on light. The other thing I wanted to talk about in my half is to talk about the influence that black holes have on matter. And so this is a movie, and it's one of my favourite movies actually because it doesn't look like very much, but it really is something quite spectacular. So here you have a bunch of dots, and when I press play it's going to move around. And it almost looks like it could just be like dust suspended in water, just bobbing around. What's amazing about it though is that each one of these is actually an entire star, more massive than our own sun, and this is a time lapse taken over 15 years or so. And as it plays, you're going to see in particular one of them is going to do a complete orbit. And let's get going. So it's going to play 3 times. If you look at this little object here, you'll see that it goes round and there's a complete loop. So do it 3 times. More. So you also notice other stars that are just kind of moving around. I guess it's going to keep playing. And what's, these are entire stars moving. You're used to thinking about planets going around the sun, but this is an entire star going around something. And of course the key thing is that this shows all the luminous objects very near the center of the galaxy. But it's not going around anything luminous. Okay, so we can take a movie like that and make precise calculations. This is done particularly by the UCLA group, the Center group, as well as others across the world. And here's a track of these objects, forming these kind of closure loops. These are kind of Newtonian orbits, which are quite far from the object that they're orbiting. And this shows, again, all of the different trajectories of the stars in the center of the galaxy. And the key thing is this one is a complete loop, and going around nothing. There's nothing that you can see that's luminous there. Whatever's there is also very compact because it can't be too big or else this star would kind of hit it as it went round, and then it gets very close to where the center is. And so we can use these orbits to deduce that actually, right in the center of our own galaxy, back to this image I showed you at the start, there is a massive black hole. And this one is much larger than the sun. This one weighs 4.1 million times the mass of our own sun. And so these monster black holes generally exist in the centers of most galaxies, and our galaxy is no different. As I said earlier on, black holes don't really suck things in, so although this is a monster black hole, it is 26,000 light years away, so it's not really a concern. Okay, so that's the things I wanted to talk about. Hopefully I'll give you some flavour for what a black hole is. So it's this region of space-time where you can go in, but once you're in, that's it, you're never getting back out to the universe outside. It has an influence on light. This was measured to be very small by the sun, because the sun, although to us is very big, gravitation is actually very small, it's not very dense. For a black hole, this is taken to the extreme, and light can wrap all the way around and produce that wonderful image I showed you. There's also an influence on matter. I talked about how you could have stars orbiting massive black holes, but you can also get matter accreting onto black holes that gets very hot as well, as another way we know that it is. And then for the second half, Ben is going to talk about how black holes can influence space and time itself. And then just another, if you haven't already, do check out the VR upstairs. Thank you.
Does anyone have any questions? Do you want to keep them till later? Yeah.
Have it done, sorry.
Go ahead.
Yeah, people on the influence on light. So that's like the visible spectrum, but does it affect all of the spectrum as well? Does it give any other influence apart from bending? Does it change frequency?
Yeah, that's a great question. Yes, so it is all light, all electromagnetic radiation. All spectrums will be done the same way. Even other types of radiation, like gravitational waves that can talk about, are distorted by that. And it also does have an effect on the frequency. So it depends exactly what you're looking at. If you have a source that's behind, it'll get kind of redshifted as it goes into the gravity, and then it'll get blue shifted as it comes back out. The other way around. Blue shifted goes in, blue shifted way out. So it won't change colour. But if the source is close to the black hole, then yes, it will appear more redder. than you would expect it, or would be already out of the visible spectrum.
Can I ask you, do black holes collapse?
Do they collapse?
Yeah,
In some sense, they are things that have collapsed. They are the final
that's
states.
what I thought, yeah.
Yeah. So if you take a star, and as I said, it's normally supported by radiation pressure. So a star is burning hydrogen and turning it into helium. Eventually, it runs out of hydrogen, and it can then burn hydrogen into a few other things. But eventually, it just runs out of fuel. It can no longer support itself against gravity. If that star's big enough, it will then just collapse in, get smaller and smaller until it becomes dense enough, and just forms a black hole. And so in general, they're permanent things. There's a slight proviso to that. If you know about Stephen Hawking's work on semi-classical theories, then there is some way they can radiate. But for a black hole to kind of evaporate, it takes much longer than the length of the universe. Its age for a very reasonably sized black hole. So they're generally very permanent objects. Something Ben will talk about is you can actually get two black holes that are very near each other, they'll orbit each other, and they will merge. And when they do so, they merge into a bigger black hole.
Just that big star, the 4.1 million times the size of the sun, will that eventually fall into the black hole?
So that is the mass of that black hole. So that black hole has contained within it 4.1 million times the mass of the sun.
It's the star going around, will that eventually get sucked into it?
So not so much sucked in. So you're right, as I said, black holes don't really suck, and that one is sufficiently far away that it just kind of orbits in a closed loop. Now, very subtly, as it does so, it disturbs the space and time. I think something Ben might mention, and it will slowly lose energy. Now, it's so far away that for that to happen is going to take billions and billions of years. So it will likely to stay there until the star runs out of fuel and dies on its own.
Thank you very much. And now, like we said, there is a VR experience upstairs for anyone who wants to try. But I think we'll welcome our second speaker first. So you guys are all set up. We don't need to change any more cables. So Ben studied in Manchester originally and is now doing a PhD in UCD in the UCD Relativity group as well. And he's going to talk to you guys about gravitational waves. Yeah, great. Okay, off you go.
Hi everybody. Just a small proviso, I am a late addition to the bill, so originally it was a different speaker, but for some reason he or she dropped out, so you're stuck with me. So I'll stand here. So following on from Niels' talk, what I'm going to talk about is waves and ripples in space and time. So we all know about waves. Generally when things move, they create waves. So if you shake a stick in a pond, you're going to create water waves. If you take a guitar string or metallic string, vibrate it back and forth very quickly, you're going to get air pressure waves, sound. How good this sound is depends on your guitar player, I must say. So even if you have electrons in an antenna, you move them back and forth, you're going to get radio waves. And if you take a very large mass, like a star or a black hole, and move it back and forth, you're going to get gravitational waves. Now the reason you get gravitational waves is the effect of gravity does not propagate outward at an infinite speed. It goes at the speed of light. So if you were to take a large mass, like a black hole or a star, move it a large distance away, a few thousand kilometers, then move it back, the effect does not propagate out infinitely, so the change in the gravitational field will not propagate outwards at infinite speed, so you actually measure a change in it. Now, this is a bit hand wavy, I know, so to actually go through and understand what gravitational waves are, we need to move beyond what we know about gravity and dive into the world of Einstein's general relativity. Okay, now this initially can seem quite complicated because the mathematics to do with general relativity is horrid. It came from the ethereal mind of Einstein, so people think it's at a level above what mere mortals can understand, and also because it comes up with some very counterintuitive consequences. But we'll dive in. So the way we can really imagine space-time is actually space and time combined into one continuum, a fabric if you will. So if you imagine it visually as just a trampoline sheet or fabric, if you drop a large mass on there, it'll actually curve and warp the space-time around it. So the big mass here would be something like the sun. If I dropped then a smaller mass that would resemble something like a planet around it, it will actually follow that curvature around it. So this is great when we're imagining the solar system, but if we're going to imagine something quite complex, when you have, for example, two very massive things like a black hole or a smaller black hole like we have here, you get this very complicated and beautiful looking orbits. Okay, so this is a bit of a plug for the black hole VR. What we actually have here in the centre is just a massive black hole, and what we have orbits around it is a very small black hole. And you can get these beautiful orbits here. But what these sort of systems can do as well is that these accelerating bodies can generate changes in curvature. These propagate outwards in a wave-like manner, and these are gravitational waves. So again, you can get these very complicated systems where you have two black holes orbiting each other, and you get this bridge curvature propagating outwards. Now, how do we go about measuring gravitational waves? Well, in water it's quite obvious. If you have a bob in water, it will move up and down as the waves propagate outwards. You'll see it, the heights increasing and decreasing. But when we come to gravitational waves, what's going to be our freely floating body? Well, if you could imagine yourself an astronaut or space dog, if you were, or two of them, if they were to measure the distance between them, as a gravitational wave would propagate through, the distance between these two freely floating observers would actually change rhythmically, increase and decrease as it passes through. Okay? Now, in practice, we don't actually lose dogs in space to measure gravitational waves. It's absurd. But how do we create our freely floating observers? Well, what we usually do in stuff like LIGO, if you've heard of it before, this is the first detector that detected gravitational waves, is that we actually use a very complicated system of tables and pendulums to actually make something that is freely floating, as it were. Or the alternative, as a future space-based detector developed by ESA, called ESA, actually just puts your detectors on spacecraft. So this is LIGO. So there's actually two detectors that comprise LIGO, one in Livingston and one in Hanford. What you see here is two massive arms. These are 4 kilometres in width. And what you have inside is some very, very expensive mirrors and a very powerful laser. It's actually, originally it was 1 megawatt. Okay? And here is an artist's impression of what LISA would look like. This is the future billion-pound spacecraft, or $1 billion, I can't remember which one it is, that will actually have the same sort of system, but it's freely floating because it's already in space. And actually, that makes it a lot easier because you don't have the effects of earthquakes, parties in nearby countries where the detector is, or the atmosphere, etc. So let's move on to the first detection. This is GW15049. Okay, you might have got that number mixed up. Please check me. This is the first detection of gravitational waves. Now, this actually came from a binary black hole merger. Now, there's many great things about this, but one thing is that the frequency is actually in the audible hearing range. Now, hopefully, if I click it, you'll hear a sound. Talk amongst yourselves.
Maybe you should make the noise.
No.
That should work.
We're definitely all going to remember this now.
We are. It's going to be great for the finish.
Okay.
I'll go back. We all heard that, didn't we?
Yeah.
It's on a loop. Okay. Now, the great thing about this, I'm going to keep it playing the loop because it's working. I want it to keep working. We call this a chirp. Okay, so the actual frequency of the gravitational waves when we've got a signal is actually audible in human hearing range. Now, this pitch is being changed slightly. If you actually hear the original, if you go online, you can find this. It's actually a much deeper sound. But again, you hear a nice little chirp. Now, the absurd thing about this is that it's not just a nice sound, is because of the amazing detection we have and the absurdity and almost witchcraft of data analysis. Trust me, it's ridiculous what they can do. We can actually detect what this came from, where it was, how far away it was. About 1 billion light years away. We knew it from a binary black hole merger, and we know, relatively speaking, where it is. or where it originated from, sorry. So, move past it. What we can also do is make lovely simulations like this, where you have, this is an idea of the strong gravitational field, these are the actual black hole horizons, and then we're actually zooming in on the merger itself. And what you see is this spirals in, your actual waves get more and more complicated and bigger until the final merger. So this is from, I will credit it, is from the Max Planck Institute. And now the important bit here is one to look at is that during this final actual merger, it released 50 times the power of the observable universe combined. So this was an extraordinary event. But because it was so far away, it was actually very minuscule by its weakest. So those LIGO arms that I showed you that were both 4 kilometers in width, those actually changed in length by a thousandth of the width of a proton. So for comparatively speaking, this is taking the nearest star outside our solar system and moving it by the width of a human hair. So this is another nice simulation. Now, this looks all amazing, I know, but I want you to ignore it because this is not the interesting bit. The interesting bit, if you actually look outside the image, you actually see the ripples in space. This is the idea of our gravitational waves propagating outwards from this extraordinary merger. So if you watch eventually, spiral in, and you start to see this gradual ripple effect here. So that's very nice. Black holes are very nice, they're very nice sources of gravitational waves. But with physicists, kind of a problem out with black holes is that they're dark. They're hard to see. We can't really observe them with a telescope. So wouldn't it be great if we could have a good source of gravitational waves that we could also see? Fortunately, nature is very kind to us. So another good source, I say good source of gravitational waves, would be a binary neutron star merger. They produce light, and actually, after their merger, they produce a supposed electromagnetic counterpart, sorry, a flash of light that we could go and detect. Now, in 2017, 2 years after the first detection of gravitational waves from the binary black hole merger, we actually detected a neutron star binary merger with LIGO, and it's a follow-up called Virgo. Now, the reason why this is interesting is this is a simulation of the sort of thing we're going to get. This sort of event is called a kilonova, so not a supernova, a kilonova. So what you see is the two neutron stars spiraling until you get a great flash. Once it merges, we detected these gravitational waves with LIGO, and with the help of Virgo, we were able to triangulate which part of the sky it was in. So then we were able to tell the Fermi telescope in this way, the Fermi Gamma Ray telescope, where this event was from, point the telescope at it, and observe the electromagnetic follow-up. And this is what we saw. So the idea is that we told it initially after the observation where it was, we point the telescope at it, and we were able to see this flash that just got fainter over the next few days. So this flash occurred around 1.7 seconds after the actual merger. So that was just a whistle-stop tour through gravitational waves. There's still a lot to be done. A lot of people in this room are working on looking at gravitational wave sources from the more complicated orbits we saw, where we have a big black hole and a small black hole. But this is not just limited to the realms of people doing PhDs and people on nice funding. You can actually help with gravitational wave detections. So one of the nice things is this organisation called Einstein at Home, and these collaborate with people with LIGO, and these, what this does, you can download a program, download it to your computer. When it's in idle, it will actually be used in calculations to help calculate gravitational wave signals from pulsars. So it's like the SETI at home, similar sort of organisation where you can set up a computer idle, and that's helped detect signals from aliens. So you can either choose one or the other, or both if you want. You can detect aliens, or you want to help gravitational waves. Either or. So that's all done from me. Question? I'll take it.
Are there any questions for Ben? Anything at all? Please. he's going to be hanging around a bit if you do have a question. You cannot ask him a question during the quiz. Sorry, that's just but thanks very much, guys. I'd like to thank both our speakers again and remind you, so we're going to take a little bit of a break before the quiz. And do feel free to wander upstairs. The guys have set up the VR so you can actually have a look at a black hole. Although you can't see them, you can still have a look at one of them. So thanks very much, guys.